Today we will speak about function, but before I start with functions, let us just review what we have done last week. So last week we did a definition of sets, and then we do some mathematical operation over sets like intersection and union, and then we discuss what we mean by subsets and set equality and the cardinality of sets. So as a revision, if you take, for example, the set U and A and B, as you can see here in the example, and we want to find A union B, A intersection B, A prime and B complement or prime, A minus B or B minus A. So if you want to intersect A with B, the union of them will be basically 1, 2, 3, 4, 5, which is everything you have in set A, combined with everything you have in set B. Now the intersection between them, the common factor between A and B are 4 and 5. Now the complement of A is basically everything in the set U and not in the set A. So we have to think about 0. It's not in A, but it is in U. Then we have to think about 6, 7, 8, 9, and 10. Same for the complement of B. So B, we will have the complement of B is 0, 1, 2, 3, 9, and 10, because these are exist in U, but not in B. Now if you take the difference between A and B, A minus B is 1, 2, 3, and B minus A is 6, 7, 8. Now, that was a quick revision of what we did last lecture. And today we will speak about function. We will speak about the mathematical definition of functions, how we define their relationship, what we mean by domain and codomain, and what we mean by image, and basically the pre-image. Then we will study as some kind of functions. They are very important for us to understand for this course and for graph theory next semester, which are injection, surjection, and bijection. What we mean by them, and how we can define whether a function is a bijection, injection, or a surjection. Then, if we have enough time, we will define what we mean by function inverse and how we can calculate it, and then we will move to function composition and so on. Before I start with the mathematical definition of function, I want you to think about this function in discrete math as any function you define in Python. In any programming language, you write a function to add two numbers, right? You define the function, and then from the main program, you call that function. You pass a value to it, you pass 1 to it, it will add another 1 to it, and return back the result. This is how functions are used in programming. The same definition we use as a computer scientist for defining a function or a procedure. It is the same function we will study in this class. So a function is basically a mapping between all the elements of the set A and B. So if you have a set A and B, both are non-empty set. You will have a function f, and this function is donated by A to B, where it gives you exactly an assignment of each element in A to every element on B. Before we do this complicated definition, let's say I want to divide this class into groups, and I will define the mapping between the group members based on one single rule. I will say each group, this is my function, each group has one student from DT255 and another student from DT249. So think about all the students in DT255 are set A, and all the students in 249 are in set B. And now I define a function to generate this kind of mapping between them. And I said each student in DT255 will be joined by another student from DT249. And this is what we mean by function. So here we write f of A equal B, which means we have now a mapping and a unique element of B in the set B is assigned by a function f to be mapped to the element in the set A. So generally, you could think about function as a mapping between elements from one set to another set. Or you could call it a transformation. Look to the example we have here in the slides. Let's say we have a set of students and we have a set of grades. And now we want to map between them. And every student get an A, we draw a line from that student to be mapped to his pre-image in the codomain, which is the grade he get. So for example, Rodriguez, he got an A, so I map him to A from set B. Patel, he got B, so I mapped him to B. Williams, he is mapped to A again, and Scott, he's mapped to A. So this is what we mean by a mapping or a transformation, and this is basically a function, sets. So a function f, thank you, because I have to do the editing. So a function A to B can also be defined as the subset of A multiplied by B as a relationship. And this is basically specifying sometimes I could have a small subset of the set A, and this subset, small elements, are mapped to the set B. So a function of f from A to B contains one and only one order pair, like A and B, for every element where A belongs, A small belongs to A. And this is satisfy the quantifier, where for all of x, x belongs to A, and for there must be at least one y exist in B, and x and y both belongs to the mapping function f. So, before you get really distracted by the previous definition, because this is more specific for a certain cases, let us take a simple example. So giving a function like f, which is a mapping between A to B, we say that f, the function, now maps any element from the set A to any element in the set B, and we call, in this case, the set A is the domain, and the set B is called the codomain. So A is the domain of the function, B is the codomain of the function. You can think about it as a computer scientist as A is basically the input you pass to a computer or a Python function, and B are the output you get from passing the elements and returning the result by the Python function. Now, in this case, if we have f of A equals to B, then at this case, once we have one element in B, in the set B, satisfies the relationship, satisfies the condition, okay? We say in this case, B is the image of A under the function f. So in this case, B is the image, the reflection of the element small a under the rule that we specify, which is the function f. As an example, if I map, for example, from DT249 Stephen, and I said Stephen is mapped to another student from DT255, let's say Sarah, okay? In this case, DT249 is the domain of the function. DT255 is the codomain of the function. Now Stephen is basically the pre-image of Sarah under the function f. Because B here, it's the image, the reflection under the function f. Now, another thing we could also use to describe the relationship between or under function, we say the range of the function f is the set of all images which basically points in the set A under the function f, and we normally denote it by the mathematical function, the famous one, f of the function or the set A. Now there is equality relationship we need to understand. Two functions are equal when they have the same domain and they have the same codomain and they have the same mapping. So each element are mapped in the same structure, the same condition, the same relationship from the domain to the codomain. And you could specify function in many different ways. And the easiest way that we can use, for example, you could describe it as a statement between the assignments of students and the grade. You can use a formula notation where f of x equal x plus 1. In this case, f of x is the function that map any element to x plus 1. In this case, if I have 1, it will be mapped to 2. If I have x equals to 2, it will be mapped to 3. If I have a 3, it will be mapped to 4. In this case, 4 is the image of a 3, and the 3 is the pre-image of 4 under the function f. Now, this is very important to stress on, because when you say under the function f, under that rule, under that condition, 3 is the pre-image of 4 because I have the function f of x equals to x plus 1. So a function could also be defined as a computer program, as a Python code. And if you want to represent it, you have like a grinder, a manual one, where you put some grains in the top as an input, which are going to be the x's. And this will result an output, and this is basically under the same rule, under the same function where f of x equal x plus 1. To understand this further, let us take an example. So in this diagram, we have two sets. We have A and we have B. Now these, the drawing, the arrows here, the blue arrows, are basically the mapping between the element A, small, to Z, from B to Y, from C to Z, from D to Z. Now once we say, what is f of A? Under this function, what is f of A? It is basically Z. F of A is Z. Now what is the image of D? Now in this case, the image of D is Z. What is the domain of the function f? The domain is A, capital. And the codomain of f is basically B, capital. And the pre-image of Y has been mapped by the element B. So the pre-image of Y is B. And what is the f of A? What f of A represent? If you take the whole set of A, what is f of A? So f of A has been mapped to two elements from B, which are Y and Z. So f of A as a total, the whole mapping is basically Y and Z. Now what are the pre-image or the pre-images of Z? In this case, the pre-image of Z has been mapped by A, it has been mapped by C, it has been mapped by D. So the pre-image of Z are A, C, and D. Let us take another example. So if we have a function which is a mapping between the set A and set B, and S is the subset of A, then the function of this small subset, this small element, can be defined as f of S, where we have S belongs to the subset S, capital. Now in this case, if I take a subset, not every element in the set A, I want to take a subset of that big set, and I take A, B, and C, and I ask, what is the function of them? What's f of A, B, and C? You will find that you need to ask yourself now one simple question. these elements to what has been mapped, to what they have been mapped in the set B. They have been mapped to Y and Z. So the answer for this equation is going to be the subset Y and Z, because these are the elements that has been mapped to those subset of element in the function, under the function f. Now the same could be applied to what we mean by f of C and D. C has been mapped to Z, D has been mapped to Z. So Z is the answer, because Z is basically the mapping between those elements under the function f. And this example resolves the second definition that we considered or we take now when we discuss a subset of the set A, how it's related to another subset of the set B under the function f. Now there is three major types of function that we need to understand. The first one is called injection. It is not the same injection that we know about. It's injection because it's map a function. The function is mapping an element from set A to set B, but it implies that we have a one-to-one correspondence. So every element from A has been mapped by an element from B. This is very important for us to understand for this class and for the second class. So here we have f of A has been mapped to Z, f of B mapped to Y, f of C is mapped to X, f of D is mapped to W. In this case, we say this is one-to-one. Or we say this is an injection. The second type is called surjection. And surjection is a function, f from A to B, where we call it as an onto. Because in this case, every element in the set B is mapped by an element from A, not the other side. Now we look to the set B and we see X has been mapped by C, Y is mapped by B, Z is mapped by D. So we are covered. All elements in B has been covered by the relationship under the function f. So we call this function onto, or we call it surjection. The third type, which is the most important for us, is called bijection. And bijection could be defined as a function f where it is satisfy two conditions. It is a one-to-one and onto at the same time. For simplicity, we need to say a function is a bijection when it is every element in A has a mapping from the set B. Now this is the first part. And the second part, when we say every element in B is mapped by an element from A. So this is what we mean by a bijection. So it should satisfy that it is one-to-one from A to B, and it is onto, which means any element in the set B is mapped by an element from the set A. Now look, A has been mapped to Z, B has been mapped to Y, C has been mapped to X, D has been mapped to W. Do you find any element in A has been mapped to the same image from B twice? No. If there is like C mapped to X and B mapped to X, this is not going to be one-to-one function. This is not going to be an injection, and as a result, it will not be a bijection. Now, same will apply to B. If B has been, for example, X mapped by C, Y mapped by B, Z mapped by A, W mapped by D, so everything in the set B has a mapping from an element from A, and we call this function onto. Now, at certain case, if you have, for example, Y mapped by B and Z mapped by B, this will not be an onto function, because there is like twice there is a duplicate relationship between the element in B and the element in A. More example. If you look to the set here, the first diagram in figure A, this is a one-to-one and not an onto. Why? Now A has been mapped by 3, B has been mapped by 4, C has been mapped by 1. So I am covered from the first side. Why it is not an onto? For a reason, because we have an element in B called 2, and this element has no mapping under this function f. So this is not an onto. As a result, this function is not a bijection because it's not an onto from the perspective of the set B. Now take, for example, figure B. In figure B, we have an onto function but not one-to-one. Why it is an onto? 1 is mapped by B, 2 is mapped by C, 2 is mapped by D, and 3 is mapped by C. Now why it is not a one-to-one? Because look here, A is mapped to 2, B is mapped to 1, that's fine. Now C is mapped to 2 again, to 3, but D is mapped to 2. So there is like 2 mapping going from A to 2, which means it's not a one-to-one correspondence, and this is not a bijection. Now when we discuss figure C, you will find that this is a one-to-one and not an onto. Why? A is mapped to 4, B is mapped to 1, C is mapped to 3, D is mapped to 2. Why it is not an onto function? No, it is. It is an onto function. It is a one-to-one and it is an onto. Because 1 is mapped by B, 2 is mapped by D, 3 is mapped by C, 4 is mapped by A. So every element in the set B has been covered by a mapping relationship from the elements in the set A. And number D, it is not one-to-one and it is not an onto for the same reason. It's not one-to-one because we have 2 elements mapped to 2. It's not an onto because 4 is not mapped by any relationship in this case. And the number C, it's not a function. It's not basically has any mathematical relationship that can be described as a function. A is mapped to 2, C is mapped to 3, and it seems to be B is mapped to 1. So this is not logical mapping between both elements.
On the last one, it's not a function because A maps to values?
It's not a function because you see there is no logic in the mapping. A is mapped to 2, B is mapped to 1, and C is mapped to 3, and A is mapped to 4. So there is like no relationship. There is no f of x equal y plus or multiply by something to satisfy this as a function.
Can I take it as a rule that f of A in that case, because f of A has 2 values, is not considered a function, 2 returns in this case?
Yeah. Because you have like f of A with 2 values and f of B with single value. So it's not logic.
The return of A wouldn't be possible.
Yeah. But if this is like from the other side, like f of A equals to 2 and f of D equal 2, that's fine. You could have from the domain 2 images in the codomain, that's fine. So how you would show that f is one-to-one or an onto? Basically, suppose that you have a function f. You need to show that f is an injective function, so you need to take x and y and arbitrary values, and you check. You need to make sure that x not equal to y, and sometimes you try when x equals to y so you can satisfy or you see the relationship satisfy or hold under the function f. Now, for injective function, you need to find a particular element in y where basically x not equal to y and f of x equal f of y. And for surjective function, you need also to choose an arbitrary element, and you see y belongs to B and find the element where x belongs to A, such that f of x equals y. So once you find this, you find that this a surjective or not a surjective function. To find why f is not a surjective, you need to find a particular value where f of x not equal to y for all elements in the set x. Let us take more examples so you can understand what and how you can employ these rules. So, for example, if you have a function f, and in the function we write it as follows. We say there is a function, and the function is mapping an element for me. So the mapping from the set A, we have A, B, C, and D in the first set, to another set 1, 2, 3, and defined by the relationship. Here I'm not giving you a generic function f of x equal y plus something. I'm just giving you the mapping. So f of A equal 3, f of B equal 2, and f of C equal 1, and f of D equals to 3. Is f an onto function or not? Before you decide, the generic rule that you could follow to solve such example, just to draw the mapping. Draw two sets, and we have in the first one, we have A, B, C, and D, and we have 1, 2, and 3. Based on the relation given by the example, f of A is mapped to what? To 3. F of B is mapped to 2. F of C is mapped to 1. F of D is mapped to 3. So what do you think? Every element now in the set B, which is 1, 2, and 3, has a mapping from an element from C or not?
Yes.
Yes. So this is an onto function. Regardless of the fact that we have A mapped to 3, f of D equal 3, f of C equals to 1, f of A mapped to 3, and f of B is mapped to 2. Regardless of, we have double mapping with the image 3 in the codomain. So this is an onto function.
It's a surjection and not an injection, right?
It is an onto but not one-to-one. Yes, it is not one-to-one. So is this function f of x equal x to the power 2 from the set of integers? Now we are taking a large set of integers. To the set of integers is an onto. The answer is no, as you can see here, because take, for example, the value 1 and minus 1. You will find 1 and minus 1 are having the same pre-image. So here in this case, when x to the power 2 equal minus 1, for example, is basically not an it's not onto function. Take, for example, minus 2 and 2. Take, for example, minus 3 and 3. Minus 2 to the power 2, 4. 2 to the power 2 is 4. So both have been double mapping. Let us now try this ourselves so we can practice and just testify the knowledge that we gain right now. There is an activity in the classroom page. You can see the same exercise if you like, or you can do it here from the slides.